Telomeres, the protective caps at the ends of chromosomes, have gained recognition as some of the most insightful biomarkers of health and longevity. Unlike chronological age, the number of years a person has lived, telomere length provides a molecular window into the biological wear and tear that accumulates in the body over time. As cells divide, telomeres shorten gradually, serving as a built-in clock that signals the limits of a cell's lifespan. Once telomeres become critically short, cells can enter senescence or undergo programmed death, contributing to aging and the onset of age-related diseases. This cellular countdown makes telomeres uniquely positioned to reflect the actual biological state of an individual more accurately than calendar years can. The idea that not all aging is equal is central to the study of telomeres. Two people may be the same age chronologically, yet exhibit vastly different biological ages depending on their lifestyle, environment, and genetic factors. Telomere length captures these differences by serving as an integrative marker of cumulative damage. Factors such as chronic inflammation, oxidative stress, poor diet, psychological stress, smoking, and exposure to pollutants have all been shown to accelerate telomere shortening. Conversely, health-supportive behaviors, including physical activity, nutrient-rich diets, sufficient sleep, and effective stress management, are associated with longer telomeres or a slower rate of telomere attrition. This responsiveness to environmental and lifestyle inputs is part of what makes telomere length such a dynamic and valuable indicator. Importantly, telomere shortening is not merely a marker of aging but may also play a causative role in the progression of age-related diseases. As telomeres shrink, their ability to protect chromosomes diminishes, increasing the risk of genomic instability, DNA damage, and cellular dysfunction. This process is implicated in a broad range of conditions, including cardiovascular disease, certain cancers, diabetes, neurodegenerative disorders, and immune senescence. Studies have found that individuals with shorter telomeres are more likely to experience earlier onset of chronic disease and higher mortality rates, even when controlling for traditional risk factors. This makes telomere length a valuable prognostic tool that can reflect not just current health status, but future disease risk and life expectancy. What adds further value to telomere measurement is its ability to capture the long-term effects of psychosocial stress and early life adversity. Research has shown that childhood trauma, neglect, and socioeconomic hardship can leave a lasting imprint on cellular aging, leading to shorter telomeres decades later. These findings suggest that telomeres retain a record of life's biological burdens, sometimes even across generations, which helps explain why they may diverge so significantly from a person's chronological age. This historical sensitivity makes them especially relevant in public health and epidemiological studies seeking to uncover hidden sources of health disparity. Modern advances in molecular biology have made it increasingly feasible to measure telomere length through blood samples, providing researchers and clinicians with an accessible tool to assess biological aging. Although there is still variability in measurement techniques and interpretation, the field is moving towards standardization, with growing interest in incorporating telomere testing into clinical practice, particularly in longevity and preventive medicine settings. Beyond its diagnostic potential, telomere biology also offers hope for intervention. Studies suggest that telomere shortening can be slowed, and in some cases partially reversed, by sustained lifestyle improvements. Physical exercise, especially aerobic activity, is consistently associated with longer telomeres, as is adherence to Mediterranean-style diets rich in antioxidants, omega-3 fatty acids, and plant-based compounds. Stress reduction techniques like meditation and mindfulness have also demonstrated telomere-preserving effects, possibly by reducing cortisol levels and inflammatory responses. These findings underscore the idea that biological aging is not fixed, but modifiable, a message that stands in contrast to the fatalistic views once associated with aging. In summary, telomeres offer a powerful lens through which to view the aging process, not simply as a passage of time, but as an accumulation of biological impacts. Their ability to reflect cumulative stress, predict disease, and respond to health behaviors makes them superior in many ways to chronological age for assessing overall vitality and health span. As science deepens our understanding of how telomeres function and how they can be protected, they may become central to a new paradigm in health evaluation, one that emphasizes prevention, personalization, and long-term resilience over symptomatic treatment. For individuals interested in aging not just longer but better, telomeres present a compelling call to action grounded in biology and responsive to daily choices.